Let's come back to the idea of equilibrium constants, because it's probably been a while since we've seen these. Let's make sure that we're polished enough to do a good job with these. Now notice that this generic reaction that I have written down here could be appropriate for a lot of different reactions that we know. And in fact, I kind of modeled this after H2SO4 gives us 2 H pluses and SO4 2 minus. So you can see this is our generic form for this specific reaction. But for the moment, let's go ahead and stay generic. So let's go ahead and write our equilibrium constant, and we'll talk a little bit about what this actually means physically. So we're going to have K, that's our variable for our equilibrium constant, and that's going to equal our reactants will be on bottom, products will be on top. So we're going to have our C plus concentration times our A2 minus concentration over our C2A concentration. Now hopefully you're spotting something right away and saying, wait a minute, you forgot something. What did I forget? Go ahead and fix this. Okay, hopefully you immediately spotted that my stoichiometry has to appear in there because I have two of these present. Now, of course, our stoichiometry always appeared there for the other species too, because remember we have our coefficient of 1. I'm just going to write it small up there, 1. And we have our power of 1 there and our power of 1 there. I'm not going to have us actually worry about that for now. So you can see that this is what it would look like. But what does that actually tell us physically speaking? Well, what we're saying is that we're going to have two different C pluses. See them here. We're going to have our central anion. See it there. And what we're saying is that we're going to pop one of these off and pop the other one off. Now, is that likely to happen all at the same time? Really, no, it's not. More likely we're going to have one pop off followed by another sequential dissociation. And the reverse process will be similar. We'll see that these are going to associate, and then once it finds another set of these in solution, it'll reassociate all the way. But really what that's telling us is that the concentration of this is going to matter even more, because we have to wait until one of these finds this in the first place. Now picture for a moment that there's a very small concentration of our green, in other words our C's. It's going to take a really long time for them to find it, right? And it's going to take even longer for a second one of these to find the already existing pair. So you can picture right away, if we have a really low concentration of C+, it's going to have an even smaller effect than you'd expect, because you have to actually get them both to associate at the same moment, or at least while one's still sticking there. And there's still going to be the equilibrium for it to pop right back apart before this one ever gets there. That's what the power of 2 is actually doing here. Now let's do the opposite case. Suppose we have a really huge concentration of these C's. Well, then what we're expecting is that this is going to be constantly finding them. And so these are going to be the predominant effect inside. This is going to be our limiting factor, how many A's we have. So you can see that at high concentration, that square actually increases how much impact these are having. That's what's kind of hiding inside of our equilibrium constant. So now that we've got kind of a physical picture of what's happening in there and how it relates to the math, I also want to point something else out. Suppose we did the reverse of this reaction. We wrote it backwards. So now we're going to have my generic ion. That's not supposed to be a carbon. I should have said that from the very start. So generic cation and generic anion. And we're going to have a reassociation process to make our C2A combination. Well, notice that when we go ahead and we write this, we do the same thing. So K will equal, we're going to have our product on top, and then on the bottom of the fraction we're going to have our other species. And this time I won't do the misdirect, I'll just go ahead and put the square in there from the start. We're going to have our A minus in there as well. And you'll notice that this is just the inverse. So whenever we reverse a reaction, we don't actually have to go through the process that we just went through if we've already done this first form of the reaction. All we have to do is flip the K upside down, and we're there.